here. All right, we're good to go. All right, so section 6.3, the central limit theorem. By the time we get done with this section, we will use this theorem called the central limit theorem to solve problems involving sample means for large samples, okay? All right, now selecting a sample from a population and calculating the sample mean is itself a random experiment. And when we select a sample from a population, ladies and gentlemen, of a certain size and collect it and compute its mean, okay, the sample mean is not going to necessarily be equal to the population mean. In fact, it usually is not, all right, unless your sample is ideally equal to the entire population itself. There's always going to be what's called a sampling error. A sampling error is a difference between your sample result and your actual population result. So like if I collect a sample, let's say I have a population of size 1 million, I collect a sample of size, let's say 10,000, and I compute the mean of that sample. And then I compare X bar with mu. Okay, will they be equal to each other? The answer is they are not going to be equal to each other. There's always going to be a difference, okay, between a sample result and a population result. This is called sampling error, all right? It's inevitable. Sampling error occurs by reason of collecting a sample that is smaller than your population. And you're always going to have some sort of a discrepancy or difference between like whatever you compute from your sample versus trying to compare it to a parameter value of the population. Okay. Now, we are going to discover that when we reach into our parent population and pull all samples of a certain size out of the population and compute the mean of each one, we're going to learn that the mean of this sampling distribution of all these sample means is indeed equal to the population mean. And the standard error, as it's most often referred to, or the standard deviation of our sample means of all samples chosen from a parent population of a certain size, and is going to be equal to the population standard deviation divided by the square root of the sample size. Okay. All right, let's take a look and try to breathe life into what just happened there on the previous slide. Suppose that a professor gives an 8-point quiz to 4 students, and the student scores are 2, 6, 4, and 8. These 4 students comprise the population for our purposes here, and the mean of this population is easily found by adding these 4 scores together and dividing by 4. So after we compute this unweighted average, we get 5 for the mean score of the entire population. The population standard deviation can be computed by using our A4 mentioned, or the formula that we've seen in the past. In computing a population standard deviation, we would get 2.236. Now, suppose we were to reach into this population of size 4, and we were to choose all samples of size 2, and for each of those samples, compute the sample mean. Well, ladies and gentlemen, if we do so with replacement, we can see that we have a large number of samples that are possible. For instance, I could choose a score of 2, put it back into the population, mix them up, and select 2 again. Or I could select 2, 4, 2, 6, 2, 8, 4, 2, 4, 4, 4, 6, 4, 8, or 6, 2, 6, 4, 6, 6, 6, 8, 8, 2, 8, 4, 8, 6, 8, 8. All right, so these are all the possible samples of size 2 that can be selected from this population of size 4. And for each of these samples, we computed the mean. So all of these guys are the sample means. X bar, X bar, okay? All right. And what we can then do, ladies and gentlemen, is we can build a distribution as to the occurrence of these sample means. and the number of times they occur. In other words, a sample mean of 2 occurs only one time, right here. So out of these 16 sample means, the sample mean of 2 occurs one time. That's what this is saying right here. The sample mean of 3 occurs 2 times. It occurs right here. If I choose 2 and then choose 4, the mean of 2 and 4 would be 2 plus 4 divided by 2, which is 3. And it also occurs right here. So the sample mean of 3 occurs 2 times. The sample mean of 4 occurs 3 times, right here, here, and here, etc., etc. Okay, so now we have a frequency distribution of all these 16 sample means here. Are we understanding this so far? What's going on? Okay. All right. Then we can actually graph this discrete distribution here. We can graph this discrete frequency distribution. And this would be the graph. The horizontal axis represents the sample mean, and the vertical axis represents the frequency of occurrence of each of those sample means. And we can see that we have perfect symmetry for this frequency distribution here. Okay, so it's bell-shaped and symmetric. All right. Okay. Now, notice if we compare the distribution's frequency or graph compared to the graph of the original population having scores of 2, 6, 4, and 8, which each occur one time. Okay, so you can see that when we graph both the population, this is the population, and this is the sample. This is the graph of all the sample means, the 16 sample means that came from that population. We can see that the graph of the sample means is bell-shaped and normally distributed, whereas the parent population's graph is not bell-shaped and symmetric. Okay. Is this just a coincidence that although the parent population is not symmetric and bell-shaped, the graph of the sample means is symmetric and bell-shaped? Just a coincidence? The answer is no. We're on to something very important in statistics here. Okay. Furthermore, ladies and gentlemen, if I find the mean of these 16 sample means, now how do I do that? How do I find the mean of those 16 sample means? I will literally add up all these means here, all these 16 means, add up all of these to all of these, and then I'll divide that by 16. So if I find the mean of all these sample means, okay, what is the mean of all those sample means? Well, as it turns out, the mean of all these sample means, and notice the notation, they use mu and then a little subscript of x bar. This is saying the mean of all sample means. The mean of all sample means is the sum of all those 16 sample means divided by 16, and notice we get 5. Ladies and gentlemen, what was the mean of our population? The mean of our population was also 5. Is this just a coincidence that the mean of the population is equal to the mean of all the sample means of all samples of size 2 that were extracted from the parent population? The answer is no. We're on to something very important. This is not just a coincidence that the mean of the population is equal to the mean of the sample means. Furthermore, let's look at the standard deviation of all these 16 sample means. When running it through the formula, we come up with this for the standard error. This is called the standard error, ladies and gentlemen, lowercase sigma sub x bar. This is the standard deviation of all the sample means. It's called the standard error. of the sampling distribution of all sample means of all samples of size 2 extracted from the parent population. This standard error or standard deviation is 1.581. Notice it's equal to the standard deviation of the population divided by the square root of the sample size. Everybody see that there? Is that just a coincidence? The answer is no. We're on to something very important here. Notice also that the standard deviation of the sample means is smaller than the standard deviation of the population. That's always going to be true because you're always dividing the standard deviation of a population by some real number that's greater than 1. Okay? That makes sense. So what's up here with the mean of the population mean equal to the mean of the sample distribution of all sample means and the standard error of the sampling distribution of sample means being equal to the population standard deviation divided by the square root of the sample size? Again, is that just a coincidence? The answer is no. That, in fact, will always be the case. And you know what guarantees that always being the case, ladies and gentlemen? It's this theorem here called the central limit theorem. The fact that the sampling distribution was more approximately normal in the population is not just a coincidence. It can be shown that as the sample size n increases without limit, the shape, the shape of the distribution of the sample means taken with replacement from the parent population with a mean of mu and standard deviation of lowercase sigma will always approach a normal distribution with a mean equal to the mean of the population and a standard deviation equal to the standard deviation of the population divided by the square root of the sample size. That's guaranteed by the central limit theorem. It's always going to be the case. Now, the amazing thing about this is the parent population itself does not have to be normally distributed or bell-shaped for this to be true. Even, ladies and gentlemen, if your population is not normally distributed or bell-shaped, as long as your sample size is at least size 30, okay, your sampling distribution of all your sample means of all samples extracted from the parent population of a certain size is always going to be approximately normally distributed. And the larger the samples that are chosen from the parent population, the more normally distributed, pronounced this distribution will become. If, on the other hand, your parent population is already normally distributed and you create a sampling distribution of all sample means of all samples extracted from such a population of a certain size, then your sampling distribution will always be normally distributed, even for small samples, sample sizes of even less than size 30. Okay. But the amazing thing, again, about the central limit theorem is even if your parent population is like plagued with outliers or is skewed, doesn't matter. The sampling distribution of sample means will always be approximately normally distributed, as long as your sample sizes are of size 30 or larger. So that's a remarkable thing about the central limit theorem here. And this consequence is ultimately the foundation which will enable us to conduct inferential statistics. Okay? All right, here's an example. On average, an American skips breakfast 50 times per year. Assume the standard deviation is 4. If a random sample of 36 Americans is selected, find the probability that the sample mean, okay, times of missing breakfast is between 48 and 51 days. Well, my sample size is 36. So, ladies and gentlemen, even if my parent population is not normally distributed, my sampling distribution will be normally distributed according to the central limit theorem because my sample size is at least size 30 here. All right. And it's this sampling distribution, which is normally distributed, that's going to enable us to answer this question here. All right. And the question is, they want us to, what they want us to do is they want us to find the probability that the sample mean is between 48 and 51 times. So you know what they want us to find? They want us to compute this probability that the sample mean number of times of missing breakfast lies between 51 days and 48 days. That's the probability they want us to compute here. So, ladies and gentlemen, our sampling distribution of sample means is normally distributed. It's normally distributed with a mean equal to the mean of the population. And the standard deviation of this sampling distribution of sample means is equal to the standard deviation of the population divided by the square root of our sample size. And since, ladies and gentlemen, it is normally distributed, we can use our normal CDF function to compute this probability because it is a normal probability. Now, we don't have to standardize the endpoints to conform to the standard normal distribution. I argued that that was something we did in the old days when we had to use the tables. But now we have our calculator, our wonderful TI-84, that basically renders that obsolete. So let's bring up our calculator here. And let's bring up the normal CDF function. All right. Now, what is going to be the mean of this sampling distribution of all sample means of all samples of size 36 that we could extract from this parent population? Well, the mean, according to the central limit theorem of this distribution, is going to be equal to the mean of the population. And what is the mean of our, what is the mean of our population here? Well, they indicated on average, an American skips breakfast 50 times per year. So that is the mean of our population. That's also going to be the mean of our sampling distribution of all samples, sample means of all samples of size 36 that are extracted from the parent population. So this mean is 50. That's guaranteed by the central limit theorem. What's going to be our standard deviation or standard error of this sampling distribution of all samples of size 30, sample means of size 30, sample sizes of size 36? That's going to be equal to the population standard deviation divided by the square root of 36. Because our sample size was 36. So this is going to be our population standard deviation divided by 6. Well, what was our population standard deviation? I think they indicated it was what? 4, okay? So therefore, the standard deviation of our sampling distribution of sample means of all samples of size 36 chosen from the parent population is going to be 4, 6. Or it's going to be equal to 2/3. All right, so here we go. So, geometrically speaking, what area are we trying to find here? Remember, the mean of our sampling distribution is 50. So we're trying to find what area underneath this normal distribution curve here. We're trying to find the area from 51 down to what? 48. We're trying to find this area of probability here. Okay, where this is 51 and this is 48. Okay. All right, so let's go get our normal CDF function to compute this probability here, or to find this area here. So second, VARS, distribution mode, normal CDF. The lower end point's going to be 48. The upper end point's 51. The mean of the sampling distribution is equal to the mean of the population, which is 50. Standard error of the sampling distribution of sample means is 2 divided by 3, 2/3. And there you go. And so, ladies and gentlemen, the mean, the probability that the mean number of times an American misses breakfast is between 48 and 51 days, that probability is about 93% chance, 0.93. Everybody understand that there, how I just did that problem. Okay. Now, the tricky thing about this that most people forget is, ladies and gentlemen, the standard deviation is not just the standard deviation of our population anymore, because they don't want us to find the probability that X is between 48 and 51. They want us to find the probability that the sample mean, which is X bar, is between 48 and 51. And therefore, we're talking about the sampling distribution of sample means here. The mean of which is equal to the population mean, but the standard deviation of which is not just the standard deviation of the population, but it's the standard deviation of the population divided by the square root of the sample size. Okay, so that's important to make sure that you have this standard deviation for your sampling distribution, whatever you compute a probability of the sample mean, as opposed to a probability of just like X, okay? So that's a common mistake. All right. Okay, let's move on here. Now, oftentimes, random sampling is not done with replacement. And as a result, we've seen that if you conduct sampling without replacement, that could affect the probability of any subsequent outcomes. And so, therefore, ladies and gentlemen, especially when your sample size is a large proportion of your population size, oftentimes we have to use this finite population correction factor in order to compute more accurately our standard error of our sampling distribution of sample means. And that correction factor is just positive square root of the population size minus the sample size. Okay, divided by the population size minus 1. All right. And this only occurs, like I said, if your sample size is very large compared to your population size. Let me give an example. Like if you had a population of size 100 and you chose a sample of size, let's say 85 from that population of size 100. Well, ladies and gentlemen, your sample size is so large compared to your population that for all intents and purposes, that would be equivalent to sampling without replacement. For that reason, we would have to make this correction in the sampling sample distributions standard error. Okay, but normally we don't have that problem because normally our population is so much larger than the size of our sample, in which case we don't have to use this finite population correction factor. So I'm not going to really make a big deal out of this correction factor because normally it's not an issue. Okay, normally our sample size is no more than like 5% of the size of our population. Okay. All right. Well, let's go to our textbook now and see if we can maybe do a couple problems here. So this will be section 6.3. Six 6.3 is entitled the central limit theorem. Okay. And as always, it's probably wise to look down through some of these examples here to gain a better foothold on what is going on. Okay, let's see here. Okay, so we'll begin right here. All right. Problem number 1 here. If samples of a specific size are selected from a population and the means are computed for each sample, what is the distribution of all these means called? Well, that's called the sampling distribution of sample means. Okay. And here would be an example up here. 20 students from a stats class each collected a random sample of times on how long it took students to get to class from their homes. All the sample sizes were size 30. The resulting means are listed below here. So there were 20 students that collected random samples of size what? 30 students, and then basically polled these 30 students and asked them how long it takes for them to navigate between home and class. And let's see here. 20 students from the stats class each collected random samples times and how long it took students to get to class from their homes. All the samples were size 30. Resulting means are listed here. So each student went on campus and polled 30 random students. We're assuming the campus has an appreciable number of students, so the population is rather large. And they basically jotted down the time it takes for these students to commute between home and class. And then they found the average of that sample. All right. And so these are all the sample means from each of these 20 students that each polled 30 random students on campus. So these sample mean times here are the mean times for each of the 30 students to commute between home and class. For instance, student one's sample of size 30 shows that on average of the 30 students that they selected, it required 22 minutes to navigate between home and class. Student two's sample of size 30 students indicates that the mean time for those 30 students to commute between class and home was 31 minutes, et cetera, et cetera. So we have 20 different sample means here, okay? 20 different sample means. And notice they also computed the standard deviation of their sample of size 30. So these are standard deviations over here. All right. Now, if, ladies and gentlemen, if we had one student, let's say that polled the entire population, and let's say that the entire population is what? Well, 20 students each polled 30 students randomly, okay? And so 20 times 30 is what? 600, right? So let's assume like the population is like 600. Suppose we polled all 600 people for their commute times, and then we found the average of that population. The average commute time of that population of size 600 should be equal to the mean of all these 20 sample means by the central limit theorem. So if you added all these up, 22 plus 31 plus 18 plus 27 plus ... plus 30 plus 29, and divided by 20, the mean of all these sample means, denoted as mu sub x bar, by the central limit theorem, is guaranteed to be equal to the mean commute time of the entire population on that campus. And the standard error, or standard deviation of these 20 sample means is guaranteed by the central limit theorem to be equal to the standard deviation commute time of the entire population divided by the square root of the sample size, which was 30. This is guaranteed by the central limit theorem. Furthermore, these 20 sample means, if you were to build a histogram out of them, you would discover that they are normally distributed. So we would discover that the sample distribution of all these 20 sample means would be approximately normally distributed in bell shape, where mu sub x bar would be right in the middle here. Okay. So all these 20 sample means here, all right, would be distributed according to a normal distribution. This is called a sampling distribution of all sample means of all samples of size 30 that were extracted from the parent population. We would have a normal distribution according to the central limit theorem. Right? That's called a sampling distribution of sample means. All right, next question. Number 2, why do most of the sample means differ somewhat from the population mean? What is this difference called? So, ladies and gentlemen, each of these 20 sample means are different than the actual population mean. If you were to poll like all 600 students and average their commute times, that population mean is different from these individual sample means. Why is that? Well, the reason why that is because of something called sampling error. Again, whenever you reach into a population and pull out a sample of size that's less than the population, and you compute a statistic from that sample, that statistic result is going to be different than the population parameter result because of what's called sampling error. If, on the other hand, you pulled out a sample from this population which was equal in size to the population, then the sample mean would be exactly equal to the population mean. But all of these sample means are different than the population mean. But the mean of all these 20 sample means would be equal to the population mean, guaranteed by the central limit theorem. So I have a question for you. Which sample mean would you put faith in as a good predictor of the population mean, of which we don't know? Do we have any idea, ladies and gentlemen? If I choose randomly any one of these sample means, like suppose I chose 26, do I have any idea as to how close or how far away from the unknown population mean 26 really is? I don't have a clue. 26 could be very close to the population mean. Maybe the population mean is like, 26.98 or something. Or it could be way far away. Maybe the population mean is like, 41 or something. I don't really have any measure as to how close or far away an individual sample mean is from the actual unknown population mean. And that's true for any one of these 20 sample means. They're all different. Some of them are a little closer to the population mean. Some might be far away from the population mean. That's because of sampling error. Now, what is the mean of the sample means? What's the mean of all those 20 sample means? Well, it would be equal to the population mean. Guaranteed. That's always true by the central limit theorem. What is the standard deviation of all these 20 sample means called? It's called the standard error. The standard error, and it's denoted as this. This is the standard deviation of all the sample means. And you know what that's always equal to according to the central limit theorem? It's equal always to the population standard deviation divided by the square root of the sample size. N. All right. Number 5, what does the central limit theorem say about the shape of the distribution of those 20 sample means? It says the distribution will be always approximately normal when the sample size is large. Our sample size was size 30, so that's considered to be essentially large enough. Even if our parent population is skewed, we can still rest assured that the sampling distribution of those 20 sample means is approximately normally distributed. Okay. All right. So as I'm going to have you do this problem here, number 7. This will be like classwork number 1. It says the average lifetime of a smoke detector, the average lifetime of smoke detectors that a company manufactures is 5 years. Now, is that saying that all smoke detectors are going to last for 5 years? It's not saying that. It's saying the average lifetime. Some might last longer than 5 years, and some may not make it to 5 years. Okay. Or 60 months, and the standard deviation lifetime is 8 months. Find the probability that a random sample of size 30 smoke detectors will have a mean lifetime between 58 and 63 months. So mean lifetime means X bar, the mean of the sample. we are going to assume that the sample is taken from a large population. And so we do not have to use the what? The finite correction factor. It can be ignored. So what you're really having to do here is you're having to compute the probability here that if I randomly select 30 of these smoke detectors, that the mean lifetime of those 30 smoke detectors will be between 63 months and 58 months. So as I'm using the normal CDF function, I want you to compute this probability for this sampling distribution. And go ahead and do that problem. Again, you're going to need to know this by the central limit theorem. You're going to need to know this fact, and you're going to need to know this fact. Okay, go ahead. Knowing those facts, using your calculator, compute that probability. Okay, so computing that the mean lifetime of this sample of size 30 smoke detectors that was selected from all of our smoke detectors, and in a population there might be thousands or millions of these smoke detectors, that sample mean lifetime is between 58 months and 63 months, is going to be computed by using our normal CDF function. The lower endpoint of which is going to be 58, the upper endpoint 63, the mean of our sampling distribution of all these sample means, and there could be thousands of sample means of samples of size 30 that you could select from this population of size, maybe even in the millions. Okay. Anyways, the mean of all those thousands and thousands of sample means is always equal to the mean of the population, which is 60 months. The standard error of all those thousands and thousands of sample means is equal to the standard deviation of the population divided by the square root of the sample size. So that's what you got to enter in for the standard deviation for this sampling distribution. Not 8, but 8 divided by the square root of 30. And when you dial that up on your calculator using your normal CDF function, you should get a probability that's about 0.895. There's your answer. And that's it, ladies and gentlemen. So the probability that a random sample of size 30 smoke detectors has a mean lifetime of 58 and between 58 and 63 months would be about a 90% chance. Okay. So there's about a 90% chance that if I select a random sample of size 30 of these smoke detectors, there's a 90% chance that the mean lifetime of those 30 smoke detectors being between 58 and 63 months, that probability would be 90% chance. Okay. All right, anybody get that computed correctly or not?
Yep.
So the key is they're talking about the probability of the sample mean, not of just X. If it was just X, our standard deviation would just be the standard deviation of the population. But this is the probability of a sample mean lying between two values. Because of that, we have to use the standard error of the sampling distribution as the standard deviation. So try not to forget that. It's easy to forget that. All right. So that one is done. Okay, let's see if we can go down and do another one here. So that's part of that's classwork one there. Okay, you can try problem number 9 here. Just roll it into classwork one. The average number of moves a person makes in a person's lifetime is 12. If the standard deviation is 3.2, find the probability that the mean of a sample of 36 people is less than 13 moves. Okay. So go ahead and compute that probability. Notice again, they want the probability that the mean of a sample of 36, of size 36, is less than 13. So be on guard for that. Okay, go ahead and do that problem. All right, so the probability that the mean of a sample of size 36 people, that the mean number of moves that they make in their lifetime is less than 13. That probability is going to be found by using our normal CDF function. Geometrically, it's the area underneath the normal distribution curve of the sampling distribution of all sample means of all samples of size 36 that are extracted from the parent population. It's going to be the shaded region down here. So the lower endpoint is negative infinity, negative 10 to the 99th power. The upper endpoint of our interval is 13. The mean of the sampling distribution of sample means is equal by the central limit theorem to the mean of the population, which is 12. And the standard error of that sampling distribution of all the sample means is equal to the population standard deviation divided by the square root of the sample size, which is 36. 3.2 divided by the square root of 36. Dial it in, bring it up, and there's your probability about 0.969. You could call it about 0.970. That would be okay. Okay. So approximately 0.970. So there's about a 97% chance that if you were to randomly poll 36 people, there's a 97% chance that the number of times they move the average number of times they move in a lifetime would be less than 13. Okay. Anybody get that?
Yep.
All right, so we're computing probabilities for what's called a sampling distribution of sample means of all samples that are chosen from a parent population of a certain size. And the central limit theorem always guarantees that this will always be true. This is always going to be true by the central limit theorem, always. Even if the parent population is skewed or non-symmetric. The sampling distribution of sample means will always approach a normal distribution, especially as the sample sizes get larger and larger and larger. Okay. All right. Okay. Let's see. Let's see what else we got here. Okay, maybe we could try one more here. Maybe you could try problem number 11. I'm just roll this into classwork 1, number 11. Go ahead and do that problem. And here we go, the probability that the mean insurance, the mean amount paid for automobile insurance by a sample of size 35 is between $1,400 and $1,410. Using our normal CDF function, the lower endpoint would be 1,400, the upper 1,410. The mean of the sampling distribution of sample means will be equal to the mean of the population, which is $1,427. The standard error of the sampling distribution is the standard deviation of the population divided by the square root of 35, 35 being the size of the sample. Plug all that in your normal CDF, and you get a probability of about 0.093. So 0.093. So if you randomly select 35 drivers and poll them as to the amount of insurance they pay for their automobile, the probability that that mean amount paid is between $1,400 and $1,410 would be equal to about 9%. Anybody get that? Is this making sense? How we're doing these here? These are computing probabilities of a mean of a sample from a sampling distribution of all sample means of all samples chosen from a parent population of a certain size. Okay. All right. So I think we can move on now. Okay, let's move on. We're good with that section now. All right, let's get into section 7.1 entitled Confidence Intervals and Sample Size. All right, inferential statistics. The big idea behind inferential statistics is trying to estimate an unknown population parameter from a statistic that we compute from a sample that's chosen from the parent population. Again, why do we even, have to bother with this? Well, because again, usually populations are in the numbers of millions and millions of elements, and we just don't have the time and or the resource to basically pull all of these elements. For that reason, we have to basically start thinking about sampling the population. But with sampling comes along for the ride a sampling error. We're going to show you how to estimate an unknown population parameter and also have some idea as to the amount of error that we have in estimating it with a sample statistic result. All right, an estimator is a statistic that is calculated from a sample to predict the value of a population parameter. For example, the sample mean is an estimator for the unknown population mean. The sample variance is an estimator for the unknown population variance. And we use a sample proportion as an estimator for an unknown population proportion. These are called point estimates. Okay. So in other words, if I did not know the mean of a population, let's say the population had a size of 1 million, okay, 1 million data points. If I did not know the mean of that population, instead of pulling all 1 million data points, which would take a tremendous amount of time, okay, that I just may not have, I'm going to reach into that population and pull out a sample. Maybe I pull out a sample of size 100,000. I compute the mean of that one sample. Ladies and gentlemen, if I had no other better guesstimate as to what the unknown population mean was, I would have to probably use the mean of that sample of size 100,000 as a point estimate to maybe say, okay, the population mean might be pretty close to this sample mean. But there's a danger in that. The danger in that is this: if I reached into that parent population and pulled out another sample of size 100,000 and computed the mean of that sample, that mean might be different than the first sample mean. So the problem is, which sample mean is the more accurate estimate of the unknown population mean? We don't know. We don't have a clue. Is it the mean from sample 2, or is it the mean from sample 1? That's the better estimate of the actual unknown population mean. We don't know that. That's the problem with a point estimate, okay? Although it's a rough guesstimate as to an unknown population parameter value, we don't have any measure or idea as to how accurate or inaccurate that guesstimate is. We're going to show you how to get around that problem. Okay. A good estimator for an unknown population parameter needs to be an unbiased estimator. And it needs to be a consistent estimator and also relatively efficient. Okay. Relatively efficient is saying that it has the smaller variance than any other statistic that we could possibly compute from a sample to try to guesstimate what the unknown population parameter value is. All right. Now, a way of trying to guesstimate an unknown population parameter by using a sample statistic result is to construct what is called an interval estimate, or sometimes we call it a confidence interval. All right. A confidence interval is a specific interval estimate of a population parameter determined by using data from a sample and by using specific confidence levels of the estimate. For example, 90% of the time, if we take a sample and produce a 90% confidence interval, the resulting interval will contain the unknown population parameter about 90% of the time. If, ladies and gentlemen, I construct a 95% confidence interval for an unknown population parameter, then if I build 95 intervals, confidence intervals for that unknown population, if I build 100, intervals for an unknown population parameter, we would expect 95 of those 100 intervals to actually contain the unknown population parameter that we're trying to estimate. If I build a 99% confidence interval, that's saying that if I was to build of 100 intervals, confidence intervals, for an unknown population parameter, that would be saying that 99 of those intervals would contain the unknown population parameter value and 1 would not contain it. Okay. So some of you thinking, why would you mess around with a 95% confidence interval to try to estimate an unknown population mean, let's say, when you could build a 99% confidence interval? Why even, mess around with a 90% confidence interval? Well, we're going to find out that there's an inevitable trade-off between the level of confidence that our interval affords us in estimating the unknown population parameter versus the width, how wide the interval is. It's a little paradoxical trade-off that we have to fathom because of the consequence of sampling error that exists between our sample and the population. All right. So a population has a fixed value for its mean or proportion. Do you agree? If I have a population, I could obviously compute its mean if I was to pull everything in the population, add it all up and divide by the size of the population, right? We know that. But ladies and gentlemen, if I was to reach into the population and pull out a sample of a certain size, then each of these sample means, okay, or sample results will be different from each other and will be different from the actual unknown population parameter that we're trying to estimate. So again, we run into the dilemma as to which sample mean would be the accurate assessment as to what the unknown population mean would be. We don't know which sample mean is the best estimate. Which one's close to the population mean or which one's far away? We don't know. Okay. But by building a confidence interval, we can not only control the level of confidence that our interval will actually contain the unknown population mean, but we can also basically control the width of this confidence interval, okay? How wide it is. In other words, the difference between the lower and upper endpoint of this interval. All right, now to build a confidence interval, we're going to have to make use of the central limit theorem and also the empirical rule that we touched base with in the past. In the sense that the empirical rule, if you recall, indicates that about 95% of our data points lie about 2 standard deviations either side of our mean. Now, they're not using exactly 2 standard deviations. They're using positive and negative 1.6 standard deviations. That's pretty close to 2 standard deviations. Okay. And if we use a 95% level of confidence in trying to guesstimate, let's say, an unknown population mean, then, ladies and gentlemen, 95% of our sample means, 95% of our sample means, okay, will be within this interval here. will be between two standard deviations below our mean of our sampling distribution and 2 standard deviations above. Okay, 95% of our sample means will be clustered around the actual unknown population mean. 5% of those sample means are going to be either in the upper tail or the lower tail of this sampling distribution of our sample means here. Okay. So another way of looking at this confidence interval is that when we build a confidence interval for an unknown population mean, we'll be 95% confident that the unknown population mean lies between here and here. Okay. All right. So in order to build a confidence interval, we have to know what level of confidence we want our interval to be, whether a 90% or a 95% or 99%, which are the most typical values for building these confidence intervals. The level of confidence we choose is going to determine, all right, what are called these critical Z values here. And these critical Z values are found by using your inverse norm function on your calculator, all right? So if we build a 95% confidence interval, our critical Z values are going to be negative 1.96 to positive 1.96. If I build a 99% confidence interval, then our critical Z values are going to be about negative 2.58 to positive 2.58. And the width of the confidence interval obviously is going to be dependent upon our level of confidence. The higher the level of confidence, the greater the width is for our confidence interval. If we want a 99% confidence interval, it's going to be a lot wider than a 95% confidence interval. If this was a 99% confidence interval here. Okay. So here's the dilemma, the little trade-off. With a higher level of confidence, ladies and gentlemen, we are more confident that our unknown population mean is going to be in the interval. But we are less precise in actually pinpointing what value the population mean would be in this interval, because we have a lot of values to choose from because it's such a wide interval. If we lower our level of confidence down to 95%, we're less confident that the population mean is even going to be in this more narrow interval. But we have more precision in determining if it is in that interval, exactly what value it is, because we have less values to choose from because it's a more narrow interval. So there's a trade-off. When you increase your level of confidence, you have more confidence that your population mean is going to be in the interval, but you have less precision. If you have a lower level of confidence, you have a lower confidence that the mean of the population is going to be in that interval, but you have more precision in determining its exact value if it is in that interval. All right, so that's an inevitable trade-off. And how to get around that little difficulty? Well, the only way to do that is to increase the size of your sample. By increasing the size of your sample, you can have a large level of confidence in your confidence interval, and yet you can also keep it narrow. All right. So the moral of the story is the larger sample you can choose from your population, the better off your results are going to be, bottom line. The more accurate they're going to be. The smaller the sampling error is going to be between your sample result and the population result. So larger sample is always better, okay? All right, so what are these confidence going to be here? How do you build them? Well, it's going to be X bar plus or minus something called your margin of error. Which is going to be X bar plus or minus your critical Z value, and your Z value is going to be dependent upon your level of confidence, times your standard error of your sampling distribution of your sample means, which is to say the standard deviation of the population divided by the square root of the sample size. That's your margin of error of your confidence interval. So your confidence interval is going to have a lower endpoint, which is going to be the sample mean minus this margin of error. And the upper endpoint of this confidence interval is going to be your sample mean plus the margin of error. normally, I mean, sometimes we do know the population standard deviation. But if we don't, what if we don't know the population standard deviation? Well, then in that case, we would have to guesstimate the population standard deviation by using our sample standard deviation as a point estimate, okay? But if we know our population standard deviation, we just use that to estimate our standard error of our sampling distribution of all sample means of all samples of size n. Okay, so this is what our confidence intervals are going to look like here. All right. And if we build a 95% confidence interval, then our critical Z value right here and right here are going to be about 1.96, according to the empirical rule, because the empirical rule guarantees about 95% of your observations lie about 2 standard deviations either side of your mean. So for a 95% confidence interval, Z is going to be approximately about 1.96. 1.96. That's the middle 95% of a normal distribution. And those values could be found by using your inverse norm function. A 99% confidence interval, your critical Z values for this formula here are going to be about 2.58. Almost 3 standard deviations either side of your mean. 2.58. All right. That's what you would use for your Z values. And like I said, we don't have to use tables to find these critical Z values for forming these confidence intervals. We can use our inverse norm function. For instance, let me show you how you would find it for a 95% confidence interval. So if we're going to build a 95% confidence interval, we want to have 95% of our sample means. We want to have 95% of them bunched up around the actual unknown population mean. So we want 95% of all of our sample means to be in this interval as far as the standard normal distribution is concerned between negative 1.96 to positive 1.96. Okay. Now, how would we get these values of positive negative 1.96? Well, we use our inverse norm function to generate those values here. For instance, according to the empirical rule, we learned that 95% of your observations lie in this interval here, 0.95. So we could use our inverse norm function to find one of these Z values. For instance, if we wanted to find the lower Z value of negative 1.96, we would go to our calculator and bring up the inverse norm function. And we would type in the area to the left of that Z value we want to find to be what? 2.5%, correct? Because 95% is the middle portion of this normal distribution curve. That leaves 5% equally allocated for the upper and the lower tails. So we would go to our inverse norm function and type in 0.025. And the mean of the standard normal distribution is 0, and the standard deviation is 1. So let's go ahead and try that out and convince ourselves that we do get those critical Z values, which are about 1.96 there. All right, so inverse norm, type in 0.025. Mean and standard deviation are 1 because it's a standard normal distribution, and you do see you get the negative 1.96. And by symmetry, this would be positive 1.96. So all you got to do is remember, ladies and gentlemen, when you're building a 95% confidence interval, your critical Z value is positive and negative 1.96. 99% confidence interval is your Z values are negative and positive 2.58. Okay. And you could also find your critical Z values for any other level of confidence, for 90% or 70% or 80%. But normally we build these intervals for 95%, 99%, sometimes 90%. All right, so let's go to our textbook. Now, it's only really going to be through doing these practice problems in either ALEKS or in your textbook where this is going to start to come into focus here. So I'm going to go to section 7.1. And okay. Number 13. If in a sample of adults it was found that 15% of the adults were left-handed, the margin of error is 2 percentage points and a 95% level of confidence. The margin of error is 2 percentage points at the 95% level of confidence. Can it be concluded that the percentage of all adults who are left-handed is between 13% and 17%? And the answer is no. This reason being is because this is a 95% level of confidence. It is not like a 99% level of confidence, okay? And so because it's less than 100%, ideally, we cannot conclude it as necessarily is true. The problem with building 100%, you probably wonder, why don't we just build 100% level of confidence, 100% confidence interval? Well, 100% confidence interval, the problem would be is that it would be infinitely wide. Okay, so that's why we cannot theoretically build a 100% confidence interval. It always has to be less than 100% because it has to have some width, okay, some finite width to it. All right. Okay. Let's see here. 7.1. Let me double check something here. One. Okay, hold on a second. We're going to check some down here. Confidence intervals here. All right. Now, okay. So, what is this margin of error here when we build a confidence interval? Well, if we were to build a confidence interval for, like I said, an unknown population mean, let's say, the confidence interval is always going to be formed by taking a sample mean plus or minus this thing called a margin of error here. And that margin of error is going to be dependent upon our level of confidence, which is our critical Z value. And that depends upon our level of confidence that we choose to build this interval for. Like I said, 95%, it's going to be 1.96. For 99% level of confidence, it's going to be about 2.58. Okay, for like 90% confidence interval, it's going to be about 1.645. But this also has to get multiplied by the standard error of the sampling distribution of all the sample means of all samples that are chosen from the parent population of a certain size. And normally we know the population standard deviation. And if we do, okay, this would be the standard error of that sampling distribution here. So again, our confidence interval, the lower end point is going to be the sample mean minus this margin of error. The upper end point is going to be the sample mean plus the margin of error here. All right. Now, an interesting thing occurs here as n gets larger and larger and larger. All right, so as n, the sample size, approaches the population size, what's going to happen is this standard error is going to get smaller and smaller and smaller. Okay. And as the sample size grows larger and larger and larger, this standard error here is going to approach zero here. And so what's going to happen is the size of your confidence interval is going to get more and more narrow. Ultimately, it'll become so narrow whereby it'll only include one value, namely the mean of your sample, which then would be equal to the mean of your population. That's because the sample size has ultimately become the population size. And obviously, when you poll the entire population, you're going to know what the population mean is. You'll be able to compute it outright. You don't have to, even mess around with a sample from the population to try to estimate or infer what it is. Okay, so you're not even going to have to mess around with it at all. Okay, so this margin of error basically determines how wide or how narrow our confidence interval is for whatever it is we're trying to estimate. Normally, we estimate the population mean. Sometimes we estimate the population proportion or a population standard deviation. Okay, but this margin of error basically indicates how much error we have between our sample result and the unknown population parameter result. And so ideally speaking, we want to have a confidence interval that is really narrow and yet also has a large level of confidence in there. The only way you can have your cake and ice cream and eat them both is if you increase the size of your sample, because by increasing your size of your sample, you drive down the standard error. The standard error value gets smaller and smaller and smaller, which decreases the width of your confidence interval, which makes us even more precise in determining the exact value of our unknown population parameter we're trying to estimate. Okay. So that's the idea. So if you can choose a large sample, always try to choose a large sample if possible. Okay, because a large sample ultimately means a smaller sampling error exists between your sample result and your unknown population result that you're trying to estimate. Okay. All right. So all right. So armed with that knowledge, okay. Number 4, what is meant by the 95% confidence interval of the mean? Okay. Suppose, ladies and gentlemen, I built a 95% confidence interval for an unknown population mean by using my sample mean. Suppose that 95% confidence interval, just for the sake of argument, looked like this. Let's say it was like 5. That's the lower end point of the interval. And let's say the upper end point is like, let's say like 9. Okay. If this is my 95% confidence interval for an unknown population mean, we could interpret it this way. We would say, and let me type this out because it's a lot easier for me to type than write it. We would be 95% confident that our sample mean, okay, no, not our sample mean. We're 95% confident that our population mean, which is unknown, would be between 5 and 9. Okay, so that's how you interpret what this confidence interval is saying here. All right, if indeed that was a 95% confidence interval for an unknown population mean, we'd be 95% confident that our population mean mu, okay, lies somewhere in here between 5 and 9. Right? That is a fairly high level of confidence. All right. Now, suppose for this same population, I built a 99% confidence interval. And suppose that my 99% confidence interval had these limits on it. So suppose I built a 99% confidence interval. CI is short for confidence interval. Okay. And ladies and gentlemen, suppose that I built a 90% confidence interval. Suppose my 90% confidence interval is like this. That's my 90% confidence interval here. Now I have a question. Which of these three confidence intervals is the widest interval? The widest. That can be found by taking the difference between your upper endpoint and your lower endpoint. Which one's the widest?
The 99.
99.
Yeah, this is your widest one. Do you agree? That's your widest interval of the three. Which one is the narrowest? The narrowest is the what? The 90% confidence interval. This one is the narrow one. All right. Why is this 99% confidence interval so much wider than, the 90% confidence interval? Well, here's why. Because, ladies and gentlemen, our margin of error, again, is equal to the critical z-value times the standard error of your sampling distribution. And the problem is that with a 99% confidence interval, your critical z-value, or a 99% confidence interval, your critical z-value is about 2.58. And for a 90% confidence interval, your critical z-value is about 1.645. So you can see clearly right now why the 99% confidence interval is so much wider than that for a 90% confidence interval, because the critical z-value is larger here for a 99% interval as opposed to a 90% interval. And because the margin of error is larger, that's going to make your confidence interval be wider, okay, than a 90% confidence interval. Okay. So you can see why now a higher level of confidence makes your confidence interval wider, because the margin of error is wider. For a lower level of confidence, your confidence interval is more narrow, all right? And so we can see that we have this inevitable paradox that exists between the level of confidence versus the amount of precision we can ascertain from our confidence interval. So what am I saying here? Well, what I'm saying is, I'm going to type this out because this is very important. Wait a minute. I can't do that. Okay. What I'm saying, ladies and gentlemen, is that if we're trying to estimate the unknown population mean mu by using these confidence intervals here, which are formed by using our sample mean from a sample chosen from the parent population. For the 99% confidence interval, I'm 99% certain that mu is in this interval. So I'm 99% confident that our unknown population mean mu is somewhere in this interval here, somewhere in here. But because this interval is so darn wide, it's going to be harder to pinpoint exactly what value in this interval that mu would be, because we have a lot of values to choose from. So even though we're more confident that our population mean is in this interval, we have less precision in determining its exact value. If, on the other hand, we lower our level of confidence down to 90%, now we're less confident that our population mean mu is even in here. We're less confident. But ladies and gentlemen, if it is in here, we have more precision in determining its exact value because the interval is more narrow. We have less values to choose from. So we have this inevitable trade-off, this little paradox here between confidence versus precision. The only way to, eliminate or to reduce this paradox or this problem between the width of your confidence interval and, the level of confidence is to increase the size of your sample. Because let's look at our margin of error again. If you increase your sample size as n gets larger, what happens to the square root of n? It gets larger. And as the square root of n gets larger, the denominator of this standard error fraction gets larger, which means the fraction is going to get smaller and smaller and smaller and actually start approaching zero. So if you increase the size of your sample, you drive down the value of this standard error, which means you drive down the value of your margin of error, which means your confidence interval is going to become more and more narrow. And yet, you'll still maintain the same level of confidence. Okay. So that's how you have your cake and your ice cream and eat them both, is to increase the size of your sample. By doing that, you can still keep your level of confidence way up there. And you can also enjoy the fact that your confidence interval is going to become more narrow. So not only are you going to be more confident that your population mean is actually in the interval, you're also going to have more precision in determining its actual value, because the interval will be getting narrower and narrower and narrower as you increase the size of your sample. Okay. So, what is meant by a 99% confidence interval for like a population proportion, if we want to use like a sample proportion to estimate our unknown population proportion? Well, essentially, again, we would say would be 99% confident that our unknown population proportion would lie in such an interval. Okay. All right, here's a good problem here. What would be the margin of error for this confidence interval that has a lower endpoint of 47 and an upper endpoint of 54? What would be the margin of error here? What would be the margin of error for a confidence interval that has a lower endpoint of 47 and an upper endpoint of 54? What do you think the margin of error would be? Well, if you have a confidence interval here, so this is your lower endpoint, this is your upper endpoint, okay, and this is the mean of your sampling distribution of your sample means here. And the margin of error is going to be equal to this difference here. That's your margin of error here. It's going to be the difference between the middle value of that interval and the upper endpoint, or it's going to be the difference between the lower value of your confidence interval and the middle value of that interval. So my question is how wide is this interval here? How can we determine its width?
Don't you just take 54 or 47 from 54?
All right, so 54 minus 47 gives us 7. Do you agree? So let me document what we just said here. The width of this interval. The width is found simply by taking your upper end point and subtracting off your lower end point. So that's 54 minus 47. And that gives us a width of 7, correct? So this confidence interval is 7 units wide. Now to find your margin of error, It's just a simple matter of taking the width of your interval and dividing it by, what do you think?
Who?
Dividing it by 2. Yep, so 7 divided by 2. And so my margin of error is going to be what? 3.5. That would be the margin of error for that confidence interval. 3.5. Okay. So the width of this interval is 7, 54 minus 47. The margin of error will be nothing more than the width divided by 2, which is 3.5. And so the margin of error is going to be 3.5. We see that there? Okay. All right. So what would be the margin of error for this confidence interval for an unknown population proportion? What would be the margin of error for number 8, this confidence interval? Lower end point 0.571, upper end point 0.623. What would be the margin of error there?
.026.
Yeah, 0.026. It's going to be the taking the upper end point 0.623, subtracting off the lower end point 0.571, and dividing that by 2. So 0.026 would be the margin of error for that one there. What's the margin of error for this confidence interval for the unknown population mean, where 23 is the mean of our sample? So what do you think the margin of error would be? It's staring right at us. It would be 0. What? 0.5, correct? That is the margin of error. All right, 0.5. Okay. All right. So all right, so you do number 12 here. I just throw it in your classwork. What would be the margin of error for this confidence interval for an unknown population mean? From 94 to 104. Compute the margin of error there for that one. All right, so the margin of error is just going to be a half of 104 minus 94. So it's going to be half of what, 10? So it's going to be 5. Okay. 5 would be the answer there. All right. Now, just a couple more problems. We don't have too much time left. We'll have to finish section 7.2 next time. But what statistic best estimates an unknown population mean? Remember, I indicated if I have no better guesstimate of an unknown population mean, what could I use as a surrogate guesstimation of what the unknown population mean is? A rough guesstimate. Anybody remember? What could I use as a point estimate for the unknown population mean? I could use the mean of a what? The mean of a blank sample. That's right. I could reach into this parent population and pull out a sample of certain size, and obviously the larger size sample you choose, the better off your result's going to be. So suppose I reach in and pull out a large sample, compute the mean of the sample as a point estimate. Ladies and gentlemen, I could use the mean of the sample, X bar, as an estimate of what the unknown population mean is. But the problem with this is that I don't know how accurate it is to being equal to the actual unknown population mean. It might be right on the money, but it could be far away from the actual value. So if I pull out a sample of size, let's say 100, compute its mean, say I get a mean of 50. Does that mean the population mean is 50? No, it doesn't mean it at all. In fact, it's probably not 50 because we have what's called a sampling error, correct? Suppose I reach in and pull out a second sample size 100 and compute its mean. Let's say I get a mean of 45. Does that mean the population mean is 45? No. Suppose I reach in and pull out a third sample of size 100, compute its mean, and I get a mean of like 56. Does that mean the population mean is 56? No. But which of those three sample means is the closer one to the actual unknown population mean? We don't know the answer to that question. So point estimates are a very rough guesstimate. You have no measure of accuracy of how close or how far away they are in guesstimating or estimating the actual unknown population mean, okay? The only way to have some sort of idea as to accuracy is to build a confidence interval, which we will take more seriously next meeting, and we'll show you how to do so on our calculator, okay? All right. Now, if we're building a 99% confidence interval, what would be the critical Z values for such an interval here? For a 99% confidence interval. I think I've already indicated for 99% our critical Z values for such an interval. I think I indicated it was like what? Positive and negative, what? 2 point, was it 2.58, I think I said. Is that correct? 2.58. We can find out exactly on our calculator. You got a standard normal distribution, and you want 99% of your observations to be in between these endpoints of this interval here. So this is 0.99 here. That leaves 1% to be equally allocated for the tails. Okay. So alpha, ladies and gentlemen, this little alpha here is going to be, this alpha here is going to be equal to 1 minus 0.99, 1 minus our level of confidence, 99%, which is going to give me 1%, correct? 0.01. All right, well, that 0.01 has to be equally allocated to the lower and upper tails of this distribution. So I would take alpha and I would divide it by what? 2. And that's going to be the lower tail area. And alpha divided by 2 would be the upper tail area. So what's 1% divided by 2? What's 0.01 divided by 2? That's going to be an area of, in here, this is going to be an area of 0.005. That's going to be this area, 0.005. That's also going to be the upper tail area, 0.005. Together, 0.005 plus 0.005 plus 0.99 is going to be 1, which is the area underneath the entire curve. To find this critical Z variant down here, which is negative Z sub alpha divided by 2, and to find this critical Z value, which is positive Z sub alpha divided by 2, we use our inverse norm function. So we grab the inverse norm function on our calculator, and we type in the area. I'm going to find this lower one, this negative one down here. So we type in the area to the left of it, which is 0.005. So 0.005. And the mean of this distribution is 0. The standard deviation is 1, being the standard normal distribution. So let's go get our calculator and find these critical Z values for a 99% level of confidence. So inverse norm. Type in 0.005, 0.1 respectively, and you do get negative 2.58. So the critical Z values for a 99% level of confidence are always negative and positive 2.58. Okay? That's about 3 standard deviations either side of your mean, in accordance with the empirical rule we've seen in the past. The answer is 2.58. Okay. How about for a 98% level of confidence? What would be your critical Z values? Well, now we want 98% of our sample means to cluster up around the unknown population mean mu. So that leaves 2% of the area of this curve allocated for the lower and upper tail equally. So what's 2% divided by 2? What's 2% divided by 2? 0.02 divided by 2. Oh, geez. What just happened here? Okay. Well, 0.02 divided by 2 is going to be what? This area here in the lower tail will be 0.01. Upper tail is also going to be 0.01. So go get your inverse norm function on your calculator and let's try this out. So for a 98% confidence interval, what would be our critical Z values? Type in 0.01, negative 2.33. Those would be your critical Z values for a 98% confidence interval, negative and positive 2.33. Okay. For a 95% confidence interval, anybody remember what the critical Z values were? For 95%. I think it was positive and negative 1.96. Okay. All right, so next time we'll show ourselves actually how to start building confidence intervals using our calculator. We do have a wonderful function that goes to bat for us, whereby we don't even have to use the formula to compute them. You can use the formula that I showed you to compute these manually, but we also have a function that can take care of a mess. Okay. All right, so I'll be on the line for another couple minutes here, and I'll open up the homework. And just keep your eye on those due dates for those things. I will extend each one, the quiz and exam, by 1 day, and also the homework by 1 day. And I'll email you that and correct the schedule and post a new schedule. All right, have a nice weekend.